AP students should understand collisions at a different level than first-year physics students in a couple of ways. So let's look here. If block A and block B are approaching each other, let's look at different things that we can look at during that collision, or different ways to actually observe what's going on. The first is if block B has velocity block VB and block A has velocity VA, we could choose, if we wanted to do the work, to look at this collision in a frame of reference that's actually fixed here on block B. And all of the initial motion would happen with block A then. So in any collision, when we're looking before the collision, and usually what we're doing in a collision is we know the mass and velocity of one block, the mass and velocity of another block, and again, we're speaking head-on collisions here. And we want to know what happens after that collision. What's the situation in the future after they collide with each other? In any of this type of collision, we can fix a frame of reference here on block B and look only at the motion of block A. We don't usually do that because we have to solve the problem then in the frame of reference fixed on block B, and then we have to take our solutions to the problem and re-encode them back into the earth frame or the normal frame of reference, and that's more work than we really want to do. The important thing about that, though, is that all head-on collisions can be generalized by looking at a head-on collision between one moving block and one stationary block, because they all can be interpreted that way in one frame of reference. A second thing this leads us to understanding is something called approach speed and separation speed, but before the collision, it's approach speed. And that is how fast these two front surfaces are closing on each other, or these two centers of mass of block A and block B are closing on each other. And without saying this explicitly, sometimes people misunderstand this. If this speed is 5, for example, and then this speed is 3, some people would say, oh, the approach speed is 2, but if you think about it for a second, that can't be. This is moving 5 feet, this is moving 3 feet, they're then 8 feet closer together. So V approach would be VA plus VB, where those are the magnitudes of VA and VB. They're not signed. We can see that the signs are indicated by the arrows. We'll get into approach speed and we'll get into separation speed later when we talk about elastic collisions. Now let's look in general what happens when A runs into B. The front surface of A and the front surface of B come together, and in real life, they're not perfectly rigid. They could be really mushy. You could put a block of clay on the front of each of them, or a long spring on the front of each of them. And as they collide, A will push B to the right, and B will push A to the left. Now, what's true about the sizes of those pushes? We know that from the third law. The third law says if A pushes on B, then B pushes back equally and oppositely on A. So F of A on B is equal in magnitude to F of B on A. And if you want to include a negative sign for direction, they're in the opposite direction, those pushes. Again, I'm mainly interested in talking about magnitudes, so we're not going to pay any attention to that negative sign to indicate direction. What about the time they interact? Well, obviously, again, since time is a scalar, the time that A touches B is the same that the time that B touches A. So that means this product, FAB times time, is equal to FBA times time. Again, magnitude, and that can only be done if these forces are constant, which in general they won't be. So for an AP student, what we want to do is we want to break the time into microscopic segments, and then we could look at the force over each of those microscopic segments as if it's constant. And what we would then do is add up all those force times time products on this side and add them up. So what we really write is this: F A on B dt equals integral F B on A dt. These products in first-year physics and these integrals in second-year physics are called impulse. So f dt, integral f dt, or ft, if f is constant, are called impulses. Now, why is impulse important? Well, if we start from the third law, looking at this collision, for any particular block, we have F equals ma. We know from what we've done so far this year that A is dv dt, so F will equal m dv dt. If we separate, we get the t over to this side, we have F dt equals m dv, and we integrate that, we can see that impulse integral shows up. And what it tells us is the integral of f dt is equal to integral of m dv, and for collisions, mass is going to be constant, so the mass comes out of that. So it's mass integral dv, which is just the change in mv, or the difference in mv. So this tells us a basic rule of collisions, that impulse is equal to the change in momentum. What this tells us up here is the change in momentum on B due to the force of A is equal to the change in momentum of A due to the force of B. So this impulse momentum relationship is what tells us that momentum is conserved in collisions. The only exception to that would be if there was an impulse from the outside. So if there's a very high friction on the ground here, and this collision takes a significant amount of time, there would be impulse on block A and block B due to external forces, which would mean that momentum isn't conserved. What we use in almost all physics is something called the impulse approximation. And that says that integral f external dt is approximately 0 for all collisions. That's true if the time is short or if the external force is small, or both. Most collisions occur over a very short time, so we use this impulse approximation to tell us that the impulse is approximately equal to 0, therefore delta mv is approximately 0 as well. Okay? So we move on from there and we look at what determines the condition of the blocks after the collision. As these two things push on each other during the collision, there's going to be squeezing, deformation of the surfaces between them. They're going to be squeezed together. That's going to take some energy. And then what determines the collision is how much of that energy comes back out from the squeezing. So what we'll look at on this to determine what happens after the collision is whether that energy is completely absorbed and stays there, whether it's absorbed and comes back out fully, or whether it's absorbed and only some comes back out. And that's what determines our different types of collisions. Our sticky collision, where they stick together, energy is absorbed. Okay? The energy is absorbed and doesn't come back, and the blocks stick together. That gives us a condition after the collision. That means that VA final will equal VB final. I think it's a very easy problem solution. Nothing complicated there. We'll have the case where the energy is absorbed and all of it comes back out. We call that an elastic collision. And the condition on that is KE before the collision of everything, sum it together, equals the KE of everything after the collision. And we can use that equation to tell us what VA final and VB final are, or we could use a shortcut that we'll see in a later video. The third situation is what we tend to call a common or everyday collision. It's where some of that energy comes back, so we can't use that. They don't stick together, so we can't use that. So we need impulse. We need another piece of data to let us find VA and VB. So what they often do is they'll give us impulse as a plot. They'll have a force versus time plot. Maybe it looks something like that. Who knows what it really looks like? And the impulse will then be the area under that curve. And it's something you can calculate, or something sometimes in a problem that's just handed to you. You know what the impulse of A on B is. By the way, this would be the force of A on B. We'd have the same plot for the force of B on A because those two impulses are equal. So if this is some number of Newton seconds, okay, it will allow us once again to calculate VA final and VB final.